Hello, this is an example video for ME313, Mechanical Engineering Thermodynamics, and what we're going to look at today is an Otto cycle example. So here's the example we'll look at. We have an ideal Otto cycle. It has a compression ratio of 9. The intake to the cycle is air at 100 kPa and 25 degrees Celsius. It has a maximum temperature in the cycle of 900 Kelvin, and it produces 75 kilowatts of power. We're going to use constant specific heat capacities at room temperature, and we're going to determine the thermal efficiency of this cycle and the rate of heat input in kilowatts. I'm going to solve this problem in EES. So if you go ahead and start up EES, this is the initial window you'll see, and you have an equations window up here. And what I'm going to do first is I'm going to go ahead and specify my unit system that I'm going to be using, SI system, and I'm going to be doing my temperatures in degrees Kelvin. I'm going to go ahead and input my initial conditions, which we were told that T1 is equal to 25 C or 298 Kelvin, and the initial pressure is 100. This is air, so I'm going to go ahead and specify what the value of R is. It's 0.287. And now I can actually go ahead and just type in the ideal gas equation. It says P1 V1 equals R times T1. And go ahead and I can actually solve that system of equations. And what I end up with, there are a couple windows. Up here on the upper right is my array table. And so this is at position 1 and my values of T, P, and V. And then any variables that are not in array form, which is the value of R right now is 0.287. So we'll just go ahead and keep moving through the Otto cycle. So we're going to go ahead and go from step 1 to 2. So I'm going to go ahead and put comments in there with double quotes. And what we know is that going from 1 to 2 is an isentropic step. And so I know that T2 over T1 is equal to, I'm going to do an isentropic relation, which is V1 over V2. And that is going to be equal to the K minus 1. So K is the ratio of heat capacities. Let me go ahead and put what that is in room temperature. That's equal to 1.4. I've introduced two new unknowns now, T2 and V2, but what we know is that V2 is equal to 1/9 of V1, so I'm going to do V1 over 9 because that's the compression ratio. And now I can go ahead and type my ideal gas equation in, PV equals RT, and go ahead and solve it. Again, let's go ahead and just expand this array table, and now I see my all my conditions at point 2. So there's my temperatures, and there are my pressures. So I'm going to go ahead and just keep moving through the cycle now. I'm going to go 2 to 3. So steps 2 to 3 is going to be the heat input, and we know at the end of that T3 was equal to 900, and we know the volume is constant. We know V3 was equal to V2. So now I've completely specified that point, and now I can again do the ideal gas equation. PV equals RT. And I've now got my third condition. So we're just kind of moving around the cycle, and we can go ahead and do our next step, which is going to be step 3 to 4, which is an isentropic expansion. And so what we know is we're going to be going to a V4 is going to be equal to the same as V1, going down to that initial volume, and this was also isentropic. And so we know that T4 over T3 is equal to V3 over V4 to the K minus 1. And let's do the ideal gas equation, PV RT. And we should have our final state now. So there's all of our conditions. Our pressures at points 1, 2, 3, 4, temperatures at 1, 2, 3, 4, and what our volume is at each point. So let's go back and look at what the problem asked for. And so what we want to know is what the thermal efficiency is and the rate of heat input. So if we want to determine the efficiency, we need to know the rate that heat goes in and out. So we'll just do some Q's and W's here. And so the heat input is step 2 to 3. And so Q in is going to be equal to the heat capacity times T3 minus T2. And I got to specify what the heat capacity is. That'll be 0.718. And that should go ahead and tell me what Q in is. So now I see here's my heat input, 130.9. It also just reiterates what CV is. So that's Q in. And Q out is going to be the 4 to 1 step, so that's going to be CV times T4 minus T1. So there's the heat output, and I can determine my efficiency. Efficiency is going to be 1 minus Q out over Q in, and now I've got an efficiency of 58.48%. So the last part for this problem was we see that it produces 75 kilowatts of power. We know the rate of heat input. We know that the efficiency is equal to the work that's produced over the net heat that goes in. Those are extensive values, so that's why I'm using with capital W's and capital Q, and W was equal to 75. So if I go ahead and solve that, I've now got Q at 128.3. So little q, that's the units on that are going to be like kilojoules per kilogram. And now what I've done is determine, since I know this is in kilowatts, which is 75, this Q is going to be in kilowatts. So big Q in is 128.3 kilowatts. And that's how we do it in using EES.